So, as sad as it may seem to you, this is our last lecture. We are having a review session Monday. At this moment, it is still scheduled for 11 a.m. I have to see if I can actually get the room before that time, so expect to see a announcement on it if and when I can finalize that room time. That is, I would like to meet earlier, but if I can't, we're going to keep the 11 a.m. time slot and then go 11 to 1, I suppose. The exam, again, is a week from today. I believe it's at 2 p.m., but check your syllabus for that. It will be online, and I have to give to you the guidelines for how to take the exam, how to submit the exam. It will be either posted as an assignment, and it will have a very specific due date, or date and time, so you only have 2 hours for the exam. Or it will be on the quizzes, so that's where you'll find it. But again, I'll be posting all those instructions long ahead of next Friday. And then also, should you have any questions and you need FaceTime or another discussion with me, email, telephone, or set up a Zoom meeting. And I have plenty of time next week to chat with you. So are there any questions before we start? No, I see none. So we're going to continue with open channel flow. And again, what we were talking about last time is, first, what distinguishes open channel flow from closed conduit flow is that we have a free surface. We did not have that in the closed conduit flow. And the water surface elevation happens to be the hydraulic grade line because you have a free surface on the open channel. Gravity is basically what's moving the fluid around in these systems. And although water may flow uphill, in general, we do know that water moves in the direction of decreasing energy. And very, very often, for most of the open channel flow problems we run into, we have hydrostatics acting. So again, the 3 laws of fluid mechanics are our same friends, no difference. And they're just applied to an open channel flow system. And we have done these before with the hydraulic jump and with the sluice gate back in some of the labs. So this should not be foreign to you. And last time we defined all of the appropriate variables associated with open channel flow. So not only the discharge, but the depth of flow, the cross-sectional area, the wetted river, and the hydraulic radius. Hydraulic radius is sometimes also called hydraulic depth. And we could also perform a momentum analysis for steady uniform flow and calculate the shear stress on the bed. And from that bed shear stress, we can calculate something called the shear velocity. And I mention a lot of these because they're all in your reading. So for the energy equation, the energy loss term for the friction losses is calculated from the Manning equation. And again, the slope that's in the Manning equation should be the friction slope, the slope of the energy grade line. But very, very often for design or to get an approximation of what's happening, we'll use the bed slope. And it's actually much easier to put a survey rod on the bed of a channel than it is to put it on the energy grade line when you're in the field. So again, this is something that we can physically start to use. The bed slope, the energy grade line, is something that we can calculate, and typically that's used within more of the computer approaches when we're looking at open channel flow. The roughness coefficient in the Manning-Zen equation is typically from a lookup table or a book. You can actually calibrate them. And this table that you're seeing on the slide is right from your book. So I have another slide with all the different categories of flow. And steady uniform flow happens to be when we have a constant discharge all the time, so it's not changing, and we have a prismatic cross-section at a constant slope. And because of that, none of the geometric properties, depth of flow Y, cross-sectional area A, wetted perimeter P, hydraulic radius RH, none of those change with distance along the channel for steady uniform flow. And in addition, in this case, we would have hydrostatic pressure distribution. P is equal to gamma H. So here is an example of steady uniform flow, and what you can see is that the bed is parallel to the water surface, which is parallel to the energy grade line. So because we have a constant discharge and a constant cross-sectional area, the velocities are the same all along the channel. The depths of flow are the same everywhere, and at steady uniform flow, the depth of flow at steady uniform flow is called normal depth. So in problems, if you're asked to calculate normal depth, that is basically telling you you have steady uniform flow. You can have a rectangular channel, a flume, for example, in the fluid slab, and you may have no flow in it. So you have the cross-section, and until you have a fluid in there, you have none of these hydraulic properties. The other type of flow that we can have, obviously, is gradually varied steady flow. So again, steady flow means the discharge is constant. But now what's happening in gradually varied flow, much like in streams and rivers, is that the cross-section geometry keeps changing. The bed slope isn't the same, the width isn't the same, the irregular geometry isn't the same. And so what that does is start to change us from where the energy slope and the water surface slope and the bed slope are the same, which is true for steady uniform flow, and steady gradually varied flow, or steady non-uniform flow as it's also called. Those three are no longer parallel. You actually saw steady uniform flow in the very first lab that occurred in the fluid slab. You had the horizontal flume with a weir at the end. Upstream of the weir, the fluid was moving. And once it came to the weir, it actually had to go up the weir and over it. The depth of flow in the vicinity of that weir was changing very dramatically as you went from the cross-section of the channel to over the top of the weir into that horse trough to weigh the water. So the flow was steady because it was constant, and what was happening was the depth of flow and the area and the velocity were all changing as we moved the water in the vicinity of the weir. A special case of open channels is a rectangular channel. And why that's special is it has a very known geometry. And that actually is a geometry we can assume sometimes in the field, or obviously in laboratory situations, in flumes, we have this cross-section. So again, with the rectangular cross-sections, we can start to describe the discharge per unit width, which is just the total discharge divided by the width of the flume. So last time we did an example using Manning's equation, and in closed conduit flow, we had friction losses and minor losses. In open channel flow, we have friction losses and minor losses. The minor losses are calculated the same in both settings. A loss coefficient times the velocity head. You can have contractions and expansions in open channel systems. You can have, for example, a pier, or a bridge, which a bridge cross-section, which is maybe much narrower than the natural channel. For the friction losses, in closed conduit flow, we use the Darcy-Weisbach equation. In open channel flow, we use the Manning equation for the friction losses. So here we have a rectangular cross-section. The width is 100 feet, and you're told that you have a discharge of 80 cubic feet per second. The Manning's roughness coefficient for the bed is 0.03. And you're asked to calculate the normal depth. Remember, normal depth means that you have steady uniform flow. So the bed slope is equal to the friction slope. And the bed slope in this case is 0.406, 0.00006. So what the question is asking is, what is the depth of flow in this situation? The normal depth. So we're going to use the Manning equation, and just like last class, we can multiply both sides of that equation by the cross-sectional area. And so now we have the Manning equation in terms of discharge, and if you recall in the problem, you were given the discharge. We want to know the depth of flow. and the depth of flow is contained here. So the area is 100 feet times YN. That's the cross-sectional area. The wetted perimeter, again, for a rectangular channel, that's not different enough. For a rectangular channel, if this is your depth of flow, then this is the wetted perimeter. So the wetted perimeter is the base width, 100 feet, plus 2 times YN, which is the length of the wetted perimeter on both sides of the channel. And so now we know what the hydraulic radius is. It's area over wetted perimeter, and that's what goes into the Manning equation on the second line of the slide. And so the discharge is given in the problem, 80 cubic feet per second. And the right-hand side, just substituting in all the numbers, 1.49 foot to the 1/3 per second. Again, very rarely will you see people put dimensions on that 1.49, but they actually exist. Times 0.03, 100 YN is the area. And then the hydraulic radius is 100 YN over 100 plus 2 YN times the slope to the 1/100th power. And because YN is buried in these terms, this defies a factoring of YN. You cannot simply factor YN out of this. So this would be a trial and error solution. Before we go to the trial and error solution, there's something called the wide rectangular channel assumption. And for rectangular channels, and maybe even some other forms, this is not a bad first guess. But it's an assumption. You always have to check the assumption. So in this case, if you look at the hydraulic radius term, which is area over wetted perimeter, this was on the previous slide. For a rectangular channel, the area is BY, and the wetted perimeter is B plus 2Y. And what we do is divide numerator and denominator by B, and that gives you hydraulic radius is equal to the depth of flow Y divided by 1 plus 2Y over B. And if 2Y over B is less than 5%, as 2Y over B goes to 0, the hydraulic radius is just going to the depth of flow. Again, this is why sometimes people refer to hydraulic radius as hydraulic depth. It's not really the depth of flow, it's a hydraulic radius. So, if we put this assumption, wide rectangular assumption, into this equation, that complex term for the hydraulic radius is now just the normal depth to the 2/3 power. And what you basically have here is YN to the 5/3 power. And now you can factor this out of the equation and solve directly for the normal depth. So the wide rectangular channel assumption made a trial and error solution a direct solution. However, once you get your answer, you need to check and make sure that you've met that requirement. So what we find is that the normal depth is 1.55 feet, and then we calculate 2y over b, and that turns out to be 0.03, which is less than 0.05, 5%. So that would be your answer, 1.55 feet. And I just wanted to show you an example of when it did work, but if it didn't work, or if you just want to start it to the trial and error, and you can code this into Excel and just use the solver to do this for you. But the wide rectangular channel assumption is a good first guess in the trial and error solution. However, in this case, if you're doing trial and error, you set up the equation with all the knowns on one side and the unknowns on the other side. So for example, this was the equation we had with the full description of hydraulic radius. And everything that we know, the 80 CFS, 1.49 over 0.03 times 100, and 0.406 to the 1/2. That's just a number. So when you rearrange this equation, this is what you get. And now for the trial and error solution, what you do is assume yn and see what the right-hand side is. And you keep guessing until you get a yn value that gives you 2.079 on the right-hand side. And again, if you had a first guess, a decent way to get a good first guess is to use that wide rectangular channel assumption. But in this case, let's assume that we didn't know or we didn't use the wide rectangular channel assumption. So here you can see we're just guessing at values of y. And remember, the right-hand side, we want 2.079. So we guessed at 1, we get 0.897. We guess at 2, 3.09. We want 2.079, so we know the answer is between 1 and 2 right now. And so what's happening is you're guessing at values of yn, and you're getting values of q, discharge. Now I plotted this graph, and yn is actually the independent variable, but I put it on the vertical axis because typically we measure the depth of flow in the vertical. And a plot of depth of flow versus discharge is known as a rating curve. And so what you're doing is you're guessing values of yn, and what you keep doing is going back and forth once you bracket it. So we bracketed the real value, 2.079, between depths of 1 and 2 feet. And so we just kept guessing until we finally got the answer. And again, because the wide rectangular channel assumption worked in this case, the answer we get by trial and error meets the answer, or matches the answer we got with the wide rectangular channel assumption. Any questions on that? Good. So, continuing with this example, but talking about something that we discussed last time. Last time I introduced the Froude number. And you've actually seen this before when we were talking about the hydraulic jump and the sluice gate. But if we had a lake, and 2 weeks from today, or actually maybe 8 days from today, on Saturday, December 19th, you take your fluid mechanics book and you throw it into that lake, what you would see are concentric rings moving away from where you throw the bucket. And these move at a velocity we're going to call the wave celerity, A. And we actually talked about this at the beginning of the semester, where that's a function of the bulk modulus of elasticity of the fluid. So in a lake, the velocity is 0. And the Froude number, as you'll see on the next slide, is the velocity over the square root of gy, where y is the depth of the water. The square root of gy is also called the wave celerity. So in this case, the Froude number would be equal to 0. And that's why you get the concentric rings moving away from the disturbance. In a river, where you have velocities, but they're not really high, so you have a small velocity, if you threw the fluid mechanics book in here, and the velocity was left to right, what you would see is a distortion of those curves. And what happens in the downstream direction, the disturbance moves in V plus A, and in the upstream direction, they move at V minus A. But in this case, V is greater than A, and therefore the Froude number is less than 1. So this is known as subcritical flow, and the Froude number is subcritical flow. Froude number is less than 1, that's subcritical flow. When you have very fast-moving water, for example, on the spillway to a dam, very steep slopes, if you threw the disturbance in here, and by fast-moving, in this case, the wave celerity is greater than the velocity of the stream. What happens is the entire disturbance is washed downstream. So nothing can move upstream. This is supercritical flow. And this is actually important when you go into calculating open channel flow or using the energy equation in river systems. How you perform the calculations when the Froude number is less than 1 is you start downstream and you make your calculations going upstream. In fast-moving streams, for supercritical flow, we have to go from upstream to downstream. So this has an effect Also, obviously with the velocity, this has a significant effect on how sediment moves, how sediment bed features form in rivers, and a lot of other things. But we need to distinguish whether we have subcritical or supercritical flow in many of the open channel applications. Many of you have heard the term 100-year floodplain. So what we do is we estimate what the 100-year flood is, and then we use the Manning equation to calculate the depth of flow in that river system, and we identify the water surface stage at that flow. That's the 100-year floodplain. So in this last example, again, this is our fruit river, and the question is, do we have subcritical or supercritical flow? We just calculated that the depth of flow is 1.55 feet. The discharge was 80 cubic feet per second. We had a rectangular cross-section that was 100 feet wide, and the depth of flow is 1.55 feet. And therefore, the velocity, which is discharge divided by area, is 0.516 feet per second. And so with the depth of flow and the velocity, we can calculate the fruit number. So here the fruit number turns out to be 0.073, and that just means that you have subcritical flow. For the hydraulic jump, if you recall, you had a horizontal bed in the lab, and you went from supercritical to subcritical. For the sluice gate, you did just the opposite. You went from subcritical to supercritical. So, what happens at exactly critical flow? When the fruit number exactly equals 1, you have critical flow. And if we look at a rectangular channel, again, the fruit number is V over the square root of GY. Some people use the fruit number squared, which would be V squared over GY. They just don't like the radical sign in the denominator. But if we substitute for velocity, discharge divided by area, and again, fruit number equal 1 is Q, the discharge, divided by A square root of GY. And now what we can do is rearrange the equation. This is a metering equation. Now you can certainly use the Manning equation for a metering equation. And all a metering equation is saying is you have this unique relationship between discharge and depth of flow. I showed you that before in another slide with the Manning equation. But with the Manning equation, one, the hydraulic radius of the cross-section can be very complex. Two, you need to know the roughness coefficient. And then you also need the slope. At a fruit number equal to 1, all that disappears. And that's why if you can create or identify in a system, an open channel flow system, where you have fruit number equal to 1, you can use that as a metering equation. That is, you have a rating curve at that location. So again, using this concept, if you know or can create a location where the fruit number is equal to 1, you've created a metering location. So this brings us to flumes and weirs. Flumes and weirs are open channel structures that create critical flow, fruit number equal to 1. What a weir does is basically create a vertical step in the bed as you go downstream in direction of flow. And again, that bed can be horizontal, a regular slope, or an adverse slope. But what you do is you raise the bed high enough such that you create a fruit number equal to 1. And what a flume does is it creates a contraction. So remember, when we were talking about closed conduit flow, and we were talking about venturis, which is a contraction and an expansion, and you had labs on venturis, when we go from a large cross-section to a small cross-section, we increase the velocity. In pipes, that results with the pressure decreasing to the maximum decrease where the throat of the venturi is. Same thing happens in open channels. When you go through a step height, what happens is in subcritical flow, the depth of flow decreases. And what happens is you steal energy from depth of flow to increase v squared over 2g. So likewise, either by changing the bed or changing the width, or both, so some flumes do both, they will create free number equal to 1. So I bring up the partial flume because, at least formally, in the course most of you will have next semester, the environmental engineering course, you will be talking about flumes or using weirs or flumes in the design of some of the water or wastewater systems. So again, what a weir does, and what you're seeing is, this is a notched weir. So in the middle, you have a really narrow section, and that acts as a weir. And you can see, you could have maybe called this a dam. But basically what a weir does is, flow is moving in this direction, and the bed of the channel might be down here. And so the weir is acting as a dam or an increase in bed elevation. And so if we looked at this in profile, here's the water surface, and then it goes over the weir. And again, this portion of the weir is an adverse slope. You have water flowing uphill physically. But that's what's happening. And on the top of the weir, is where we have root number equal to 1. And so all we have to do is measure that depth of water on top of the weir, and we know the discharge. So there's many, many different types of geometries. The most common ones we will typically use are a V-notch, a full rectangular weir, or a contracted rectangular weir. But they're the most common, but there are many types. And there's a difference between a sharp-crested weir, in which you have a very narrow weir width along the direction of flow, versus one that's really large. So in both of them, you have fruit number equal to 1. But the difference between the sharp-crested and the broad-crested is you have additional friction losses over the top of this broad-crested weir. So for example, if you have a culvert under the road and you have a really big flood coming, a lot of water is going through the culvert, but then the water starts to increase upstream as the flow increases and ultimately goes over the top of the road. That road is acting as a broad-crested weir. And so there are ways to define which is sharp versus broad-crested based on the depth of submergence, H, and the width of the weir in the direction of flow, A. And there are some very simple weir equations we use. So if you have a rectangular weir, basically T is the top width perpendicular to the flow. H, I showed you in a previous slide, is the depth of water from the weir crest up to the water surface upstream of the weir. And I want to go back to these slides. Upstream of the weir, that water surface is the EGL. In the vicinity of the weir, what you see is the water surface is starting to decline or decrease. It's no longer horizontal. And what's happening is, in that vicinity of the weir, you're converting the full depth of flow from the bottom of the channel to the top. You're starting to convert some of that to v squared over 2g. And that's why the water surface starts to plunge. And so H is measured from the weir crest to the water surface elevation upstream, because H is a measure of the total energy you have available to push water over that weir, or through a flume for that matter. So these are very simple equations. And again, what you have is discharge versus elevation. That's a rating curve. For the triangular weirs, similarly, you can have a broad-crested triangular weir or a sharp-crested triangular weir. Very simple equations, and theta is the full opening angle of the weir. It looks something like this. In comparison, well, if we use, for example, What's the depth of flow for a 45-degree triangular sharp-crested weir flowing at 4 CFS? So this is the equation for the sharp-crested triangular weir. Our angle is 45 degrees. And so we would take this equation. We know the discharge, 4 CFS. And we know theta, 45 degrees. And so all we're doing is calculating or rearranging this equation to solve for h. So in this case, the total depth of water above the crest of this V-notch weir. So if your V-notch looks like this, this would be the depth of water. Not in the weir, because remember, the water depth in the weir is much less than this because it's in that location where the water surface is curving downward to go through the weir. And if we use the same weir, 45-degree V-notch weir, and we were asking the question, well, what's the rating curve? What you would do is vary h and calculate q. So again, this is the equation of our sharp-crested V-notch weir. And now what we're going to do is put in everything we know. It's a 45-degree weir, and we're just going to put in values of h in the spreadsheet and calculate the discharge. So that's the rating curve, and again, it's something you can plot. A function like this is called a monotonically increasing function. That is, as you increase one state variable, the other state variable increases. Monotonically increasing function. So that takes us to the last few slides for the semester. Partial flume is something you will see again in next semester. They'll be talking about them, so you should at least be familiar with them. And what the partial flume does, it's named after Ralph Partial, who was a professor at Colorado State University, and built the initial prototypes for these, and they caught on like wildfire. So again, what you do is create a contraction, the flume. But you also have something that acts like a little rise in the bed. So again, just like what a weir does, a weir increases the bed elevation. And you're doing both the contraction and this little increase in the bed to force the flow to go to fruit number equal 1 in the throat. And when you know that, if you look in this flume, you measure the depth of flow, and again, with a very simple equation, it then translates into discharge. So again, you can put weirs and flumes in any setting you would like, and they help you measure the discharge. At the Stormwater Center on campus, we use weirs at the end of all the pipes, so we can measure the inflow hydrographs to all of our systems, and we can measure the outflow hydrographs to all of our systems. In natural channel systems, for example, a 20-foot wide river, one, you just can't put a structure out there. You can't just put in a weir because you want to. You would need permits to do that, even temporarily. And so very often in open channels, we actually may be stream gauging, just like Professor Kinnan had you do in ENE 400. You would go out and measure the velocity across different locations across the stream, multiply that by the cell of each, where you're measuring cell width times the cell depth, the water depth in each cell times the velocity, and you calculated the discharge across the stream. It's a lot easier with the flume. So this is a wastewater treatment plant, and you can see where this flume has been installed. And they're very, very common. Typically, they're located downstream of where you do some initial primary treatment. So for example, after the comminutor or barbinutor, where you're grinding everything up, and possibly after primary settling. So you don't have a lot of things that can clog this up. And then there are many other types of flumes. So I'm just showing you a trapezoidal cutthroat flume, and the other one on the right is an H flume. So very often in small streams, or where we're trying to measure stormwater flows in small swales, we'll install an H flume. And one reason why you might pick one flume over another These are both rating curves, where if you measure the depth of flow, you get the discharge. If you're interested primarily, for example, in high flows, then either of these would work fine. If you're interested in the low flows, the H flow would have a bigger change in depth of flow for a small change in Q. So it's giving you a better estimate of the discharge than the trapezoidal, because in trapezoidal, a very small change in depth of flow, you have a big change in discharge. So you're not getting a lot of precision at the low ends with the trapezoidal flow. And so that's the whole idea of selecting years and flumes. You have an objective. And if your objective is to measure from very, very low flows to very high flows, you could actually have, for example, a compound weir or a compound flume. So you have a triangular notched triangular. You have a triangular notched inside of a rectangular. And what the triangular notch would give you is really good precision on the low flows. And then as you get to higher flows, again, what you're trying to do is, for any change in depth of flow, get a pretty good estimate of what the discharge is. You don't want to have there to be large variabilities. And again, in these open channel systems, these flow systems, very rarely is the water just sitting there nice and stable. It's always bouncing around because of waves, because of wind, because of waves created by the contraction itself, just like when you see bow waves and stern waves off of a ship. These features, wherever you have a change in the geometry, create waves. And so the water level is always bouncing around, and you're trying to get an accurate reading of the depth of flow, and therefore the discharge. And if your depth of flow is bouncing around, and you have a very flat rating curve, you have wide springs, wide ranges in your estimates of the discharge. So I believe that's the last slide, and I'll open it up for any questions you may have in the remaining 15 minutes. And if you don't have any, then we'll let you go. Are there any questions? No questions. 50 people signed on, which is full class.
So the final exam is still consistent with the chapters labeled in the syllabus from the beginning of the year, correct?
I honestly had a tough time hearing that. Could you please repeat that?
Yeah, so can you hear me well now? No?
I can't hear you. Could you just repeat your question? Can you repeat your question?
Sorry, I'm having a little trouble with the audio. Is that better?
Yes, I can hear you now. Just repeat the question, please.
Yeah. So I was just wanting to double check. So the syllabus that you posted at the beginning of the year, the final exam still going to consist of the third section, all the chapters labeled before that final exam, correct?
The final exam, or exam 3 as I like to call it, is not cumulative. It'll start where the last exam ended, and I have to go back to memory, but if I recall, on the last exam, you were responsible up through the boundary layer.
Yep, okay. I just wanted to double check.
Yeah, so there's no overlap, but of course, you can't forget anything from, the first part of the course, like fluid properties. So some of the stuff you just can't forget, but it's all the material since the last exam. Any other questions?
I had one question from one of the students about the format of the exam. Is that you assume, could you please describe a little bit?
I thought I did that at the beginning of class.
Ah, okay.
I will be sending out instructions on the exam format because it's all online. And I do want to remind you that teaching evaluations and TA evaluations are available, and I believe they close today. So if you have any venom that you want to release, do your teaching evaluations for the TAs first, and then you can do the professor next. But seeing no other questions, I know it was a challenging semester for all of us. Thank you for sticking it out, and hopefully I'll see a lot of you Monday morning in the review session.
There's a question about the crib sheet.
How will the crib sheet work? The crib sheet works as it did in every other exam. You can have one crib sheet, and you can write on any of the 6 sides. And the idea is that you're not, even though you're in your own room, you're not flipping through. If you have to do that, then you really didn't study hard enough. So I would like you to still have one crib sheet, and that's what you can be looking at on your desk. Obviously, all we can do is see your camera and you and your workspace from your camera, so that's all we can see when we're monitoring the exams.